Hello students, welcome to EPG Pathshala. I am Dr. Abhilasha Shauri from Manav Rachna International University, Faridabad. Today we are going to talk on module General Introduction to Chromatographic Techniques, Definition, Principle and Classification. This comes under the paper Chromatographic Techniques 2. After completing this module, you should be able to understand the fundamental concepts of separation technique, chromatography, to learn the general principles behind chromatographic separations, and to learn about various types of chromatographic separations. We start here with the definition of chromatography. It is a powerful technique that can be used to separate mixture into its components with great precision. In fact, it can be used to distinguish between two compounds that are very similar in molecular mass or charge. The separation is achieved on the basis of differences in the distribution of sample components between two different phases, stationary phase and mobile phase. The sample mixture to be analyzed is applied to a stationary phase and the mobile phase flows through it. It mobilizes and elutes the analyte out of the stationary phase at different time intervals, and that is how the analytes into the mixture are separated. History of chromatography. The first chemist to develop the chromatography was a Russian botanist, M.S. Sweat. He developed this useful technique in 1903 to separate plant pigments under gravity using a calcium carbonate column. Sweat also coined the term chromatography from the Greek word chroma, meaning color, and graph. Chromatography was recognized as a powerful technique that can separate a mixture into its components with great precision. In fact, it can be used to distinguish between two compounds very similar in molecular mass or charge. With the use of right materials and operating conditions, chromatography is capable of purifying wide range of soluble or volatile substances. In all types of chromatography, the mixture to be analyzed is applied and allowed to adhere to a stationary phase material known as an adsorbent. A stationary phase is usually a bonded phase that is covalently bound or immobilized to the support particles or to the inside wall of the column tubing. The mobile phase is the phase which flows through the stationary phase in a definite direction. Mobile phase may be a liquid, as in liquid chromatography, or a gas, as in gas chromatography, or it can be a supercritical fluid, as in supercritical fluid chromatography. The mobile phase moves through the stationary phase in the chromatography column where the sample interacts with the stationary phase and is separated because the different components of the mixture adhere to the adsorbent with varying degrees of strength. They also migrate different distances through the adsorbent as the eluent flows through it. In other words, the components that adhere more strongly to the adsorbent travel more slowly than those with weaker adhesion. In effect, this process separates the various components of the sample mixture into individual compounds that can be further analyzed. The chromatographic separation is visually assessed through chromatogram. If the separation is optimal, different peaks or patterns on the chromatogram correspond to different components of the separated mixture. The characteristic time taken by a particular analyte to pass through the system, that is, from the column inlet to the detector under set conditions, is specific and characteristic of an analyte and is known as the retention time. Equilibrium distribution of analytes. Analyte molecules may exist in free state, that is, completely dissolved in the liquid or gaseous mobile phase, or may exist in bound state, that is, adsorbed on the surface of the solid stationary phase. However, an analyte is in equilibrium between the two phases, that is, the stationary phase and the mobile phase. The equilibrium between the free and adsorbed states depends on the following factors: the polarity and size of the molecule, polarity of the stationary phase, and polarity of the solvent. The size, shape, and polarity of molecules is their characteristic feature and is determined by their own chemical structures. This equilibrium can be changed by selecting different stationary and mobile phase combinations. If the molecule A dissolves faster, it tends to spend more time in mobile phase. It will be carried through the stationary phase faster and move farther in the given time. Adsorption and solubility of molecules can be manipulated by choosing the appropriate stationary phase and mobile phase to obtain good separation. The equilibrium constant K is termed as the distribution or partition coefficient. It is defined as the ratio of molar concentration of analyte in the stationary phase to the molar concentration of the analyte in the mobile phase. The differential distribution of various components between the two phases determine the rate of migration of different compounds in a mixture and result in their separation from each other. Classification of chromatography. The classification of chromatography is based on different criteria. Number 1, purpose of chromatography experiment. Number 2, geometry of stationary phase and support used. Number 3, physical states of stationary phase and mobile phases. Number 4, principle of separations used. Number 5, polarity of stationary phase and mobile phase used. On the basis of purpose of chromatography experiment, we can classify the chromatographic separations as preparative chromatography and analytical chromatography. In preparative type of chromatography, the purpose is to separate the components of a mixture for further use, and it is thus a form of purification. Usually, the amount of sample injected or applied is larger, and the separated and pure components are collected for further use. The desired component of sample is retained. This is also exclusively applied in column types as preparative column chromatography. Analytical chromatography. This type of chromatography seeks to measure the relative proportions of analytes in a mixture. The sample size applied or injected is very small, and the purpose of this is to identify and analyze the components in the sample and to quantify their individual concentrations in the sample. On the basis of physical states of stationary phase and mobile phases, we can classify the chromatographic processes as solid-liquid chromatography, in which stationary phase is solid and mobile phase is liquid. The sample is adsorbed on the solid stationary phase material, and separation occurs on the basis of differential solubility of sample components or analytes in the mobile phase. Another form is liquid-liquid chromatography. In this type, both the phases, that is, stationary phase and mobile phase, are liquid, but of different polarities. The stationary phase liquid is in form of a thin film coated over an inert solid support. This separation occurs on the basis of differences in partition coefficients of analytes in the two phases. Another form is gas-solid chromatography. In this type, the stationary phase, which is an active solid adsorbent in powdered form, is filled in a tube. An inert gas like helium is used as a mobile phase or carrier gas. Then the fourth classification under this category is the gas-liquid chromatography. A carrier gas an inert gas is used as a mobile phase and stationary phase comprises of a non-volatile liquid coated as a thin layer on an inactive solid support or on the inside walls of the capillary tube. The compounds are separated according to their partition coefficients. On the basis of principle of separation, the chromatographic processes can be classified as number 1, adsorption chromatography. In adsorption chromatography, the stationary phase is a solid material and mobile phase is either a solid, as in solid liquid chromatography, or a gas, as in gas solid chromatography. The basis of separation is difference in solubility of molecules in mobile phase by virtue of their polarity. Another form, second, is partition chromatography. In partition chromatography, the stationary phase is a liquid supported on an inert solid, while the mobile phase is either a liquid, as in liquid-liquid chromatography, or gas, as in gas-liquid chromatography. Another form is ion exchange chromatography. In this type, the stationary phase is an ion exchange resin on which the ionic sample components bind electrostatically. The resin is either cationic or anionic. The mobile phase is a buffer of predetermined pH. The buffer serves to weaken the electrostatic interactions between the analyte and the resin and elutes it out at a particular pH. Another form is molecular exclusion chromatography. It is also known as gel permeation, gel filtration, or size exclusion chromatography. In this, the stationary phase is a porous gel with a specific pore size. As the mobile phase passes through a porous gel, large solute molecules pass through the void spaces while smaller molecules are entrapped in the pores of gel beads. This allows the larger molecules to pass through the column at a faster rate than the smaller ones, and thus the molecules are separated on the basis of their molecular size. Yet another type of chromatography is affinity chromatography. It is highly selective type of chromatography that is based upon the specific interaction between analyte molecules and another compatible molecule that is immobilized on a stationary phase. For example, for separation of antigens and antibodies may be immobilized on a matrix that forms the stationary phase. When sample consisting a mixture of proteins is passed through the column, only the specific antigen is bound to the antibody immobilized on the stationary phase. This antigen can be extracted either by changing the ionic strength or pH or through dialysis. Finally, on the basis of polarity of stationary and mobile phase used, we can classify the chromatographic process as normal phase chromatography and reverse phase chromatography. In normal phase chromatography, the stationary phase is polar in nature and the mobile phase is nonpolar. Hence, the nonpolar components are eluted out first and polar compounds later, as they have greater affinity towards the stationary phase. In reverse phase chromatography, the stationary phase is nonpolar and mobile phase is polar in nature. In practice, this reversed phase chromatography is highly used in routine analysis, and most of the substances like drugs, etc., that are used in daily life are polar in nature. Principles of adsorption planar chromatography. In the planar adsorption chromatography, the stationary phase commonly used is paper or a thin adsorbent layer on which the sample mixture is adsorbed. The mobile phase rises with the capillary action within the spaces of the porous adsorbent material due to the forces of adhesion, cohesion, and surface tension. Solutes dissolve into the solvent, but their extent of solubilities are different. Polar molecules dissolve readily in polar solvents and vice versa. Thus, the separation of components depends on both their solubility in the mobile phase, their differential affinity to the mobile phase, and the stationary phase. This figure depicts the method of performing ascending paper chromatography. The solvent rises up due to the capillary action and dissolves the solute components through its way upwards. The molecules that dissolve early rise up high on the chromatogram and their RF values are greater. The chromatographic paper is made up of cellulose and its structural composition helps the analytes to get adsorbed on its surface and immobilize readily. RF value. The separation in planar chromatography is based on the rate of migration of the molecules, and this can be quantified as RF value, which is the retention factor, also called retardation factor or a resolution front. In the RF is defined as the ratio of the distance traveled by the component to the distance traveled by the solvent. If RF value is 0, this indicates that the solute tends to remain in the stationary phase and has zero solubility in the mobile phase. In other words, it does not migrate much to the greater extent as compared to other molecules running with it in the parallel. If RF value of a compound is near to 1, then the solute is said to be highly soluble in the mobile phase and has no affinity for the stationary phase. This figure elaborates the determination of RF values. It can be calculated as the distance traveled by the compound divided by the distance traveled by the solvent. Planar chromatography can also be used to separate compounds in two dimensions. The chromatographic run in first dimension separates the components of mixture that have distant RF values. The second dimensional run is usually accomplished with solvent of different polarity to further separate the compounds which have very similar RF values. Thin layer chromatography is quite simple and similar to paper chromatography. In this, the adsorbent material, usually silica or alumina, is coated on a flat plate made of glass, aluminum foil, or any other inert support material. The principle of separation remains same and the analyzed on the basis of their RF values and visualization on the chromatogram. Visualization methods in planar chromatography. In planar chromatography, the identification of analyte molecules is done on the basis of its visualization. If the molecules are in itself chromogenic, then they can be observed directly on the chromogram. However, if molecules are colorless, different visualization methods can be used to render the sample spots visible. Such visualization methods can be ultraviolet light. Many compounds fluoresce under the ultraviolet light, so we can keep the chromatogram in the ultraviolet light and these fluorescing molecules can be visualized. Then there are certain molecules which can be stained using the iodine vapors. Certain color reagents are also used to stain the spots of the mixture. Reagents that selectively stain the spots while leaving the others unaffected are very helpful in recognizing, identifying and visualizing the analytes. Column chromatography. In column chromatography, the sample mixture is passed through a column packed with stationary phase material. The mobile phase is passed through the column at a certain flow rate. Using proper solvents and packing conditions, the components in the sample dissolve in the mobile phase and travel through the column. The analytes which are dissolved early are eluted out of the column first, then those which are dissolved late, resulting in the desired separation. Here we can see a column packed with stationary phase material. The sample mixture is loaded in the column and its components are dispersed throughout the stationary phase. As the mobile phase solvent passes through it, molecules elute out separately from the column and can be collected in separate fractions. The eluent is analyzed through a chromatogram, which is a graphical representation of retention time of analyte versus detector signal. The quantitative measure of separation of analytes within the column is given by the term retention time. It is defined as the time taken by the sample to travel from the injection port through the column to the detector. The migration rate of an analyte on a column is given by the retention factor. It is also called the capacity factor. The value of capacity factor can be derived from retention time of analyte and retention time of the mobile phase obtained from a chromatogram. The formula is herein given. If the retention factor of an analyte is less than 1, the elution is said to be very fast and accurate determination of its retention time is very difficult. Analytes having high retention factors, about more than 20, take too long to elute out from the column. Thus, the ideal value of retention factor is said to be for an analyte between 1 to 5. In order to understand the process of equilibration of components inside the chromatographic column, it is supposed to be comprised of a large number of separate layers called theoretical plates. Equilibration of all analytes is said to occur between the stationary and mobile phase in each of these plates. The analyte from one plate to the next after equilibration at every step moves down the column until eluted out. Theoretical plates refer to the length of the column that allows one complete equilibration of sample in the stationary phase. Height equivalent to theoretical plate HETP is defined as the length of the column necessary for the attainment of compound distribution equilibrium. It is used to measure the efficiency of the column. If the length of the column is L, then HETP can be calculated as length divided by N. Theoretical plate number and HETP are widely used as a measure of resolution in gas liquid chromatography and in high performance liquid chromatography. The figure shows 3 peaks in the chromatogram and the relationship of number of theoretical plates in the column to their shape. It can be observed that increasing the number of theoretical plates, band broadening can be reduced and sharp peaks can be obtained. This chromatogram shows peaks of two analytes A and B, of which retention time of B is greater and it is eluted out later from the column. The number of theoretical plates inside a column can be determined from a chromatographic peak. N is given as 16 into retention time of the given analyte divided by its peak width. Also, using the peak width at half height, we can derive the N. The formula is given herewith. Resolution. The efficiency of separation of any two components through the column is given by the resolution. The formula is given here. Resolution R is equal to twice of retention time of B minus retention time of A divided by peak width of A plus peak width of B. If the value of R is equal to 1, the separation is said to be 97.7% complete. Thus, the overlap of the peak is only 2.3%. Whereas, if the value of R is about 1.5, the overlap is reduced to 0.2%. Unresolved peaks are also called fused peaks. Resolution and optimal separations are characterized by sharp and symmetrical chromatographic peaks. The peaks that are not sharp refer to band broadening. These are characterized by broader base and shorter height. The efficiency of the column can thus be judged by chromatographic peaks that are obtained on a chromatogram. This figure shows a chromatogram in which many of the peaks appear to be fused, indicating incomplete separation of certain components of the mixture. Fused peaks lead to band broadening and are the result of inefficient separation. Column efficiency and band broadening are directly affected by N and HETP. The factors that affect the column efficiency can be given by Van Demeter equation for plate height. It is HETP is equal to A plus B by V plus C into V, where V is the average velocity of the mobile phase and A, B, C are the factors which actually contribute to band broadening. A is the eddy diffusion that accounts for random movement of analyte molecules through the column. B is the longitudinal diffusion due to the concentration of analytes more into the center as compared to the walls of the column. C is the resistance to mass transfer due to the time taken by the analyte to equilibrate between the stationary and the mobile phase. A, B and C are the three major factors which contribute to band broadening due to uneven rate of migration of analyte through the column. The relationship between HETP and average linear velocity of mobile phase can be given by Van Demeter plot. This plot suggests that slight increase in mobile phase velocity or flow rate decreases the HETP and thereby increases the column efficiency. Thus, the plot can be used to determine the optimum mobile phase flow rate. Good resolution thus can be obtained by increasing N by lengthening the column, that leads to an increase in retention time and decreasing the band broadening. Reducing the height equivalent to a theoretical plate by reducing the size of the stationary phase particles. Thirdly, by controlling the capacity factor K, separations can be highly improved. Then changing the temperature in the gas chromatography can also give us good resolution, and thereby changing the composition of the mobile phase in the liquid chromatography can help to achieve good resolution. Finally, the factors that can be adjusted to increase the resolution while using column chromatography are increasing the column length, decreasing the column diameter, decreasing the flow rate to certain extent, packing the column uniformly, decreasing the sample size, selecting proper stationary phase, selecting proper mobile phase, and using appropriate pressure. So students, let's now summarize what we have learnt in this module. The chromatographic techniques can be applied to separate large number of organic and inorganic compounds with great efficiency. The separations depend upon the nature of analytes to be separated. Selection of appropriate combination of stationary phase, mobile phase and other conditions is mandatory for efficient separation. Thank you.